Hello students, so let's discuss band theory of electrical conductivity, and this theory is very important. Okay, so listen very carefully. Band theory mainly explain about conductors, insulators and semiconductors. In solid, there are two types of bands, conduction band and valence band. Let's discuss by taking the example of silicon. Now we know that the atomic number of silicon is 14, and this is the ground state electronic configuration of silicon: 1s2, 2s2, 2p6, 3s2, 3p2 and 3d0. Yes, and these are the valence shell orbitals of silicon: 3s, 3p and 3d. So here there are two types of valence bands. The first one is that this 3s and 3p orbitals which have electrons, and this orbital 3d which doesn't have electrons. Yes, so because of having electrons, these orbitals are heavy, and because this orbital is empty, therefore this orbital is light. Yes, since these orbitals are heavy, that's why they are placed at the lower side, and since they are light, and therefore they are placed at upper side or placed above. Yes, now let us take this as what this is what nucleus, and we know that electrons are revolved around the nucleus. So this band is for 3s, this is for 3p, and this is 3d. Yes, now we know that here the 3s and 3p orbital have what? Electrons. So there will be a attractive force between these electrons and with this nucleus. Yes, so it will pull these orbitals towards itself. Therefore these orbitals will be placed at the lower side. Now here 3d is 0, that means there is no electrons in 3d orbital. That's why there will be no attractive force between this nucleus with this 3d orbital. Yes, so this 3d will be little bit far from this 3s and 3p orbital. So this is the band of 3s and this is 3p, and this is band for what? 3d. Now this 3d band is empty, there is nothing. So this empty band is known as what? Conduction band. And here this 3s and 3p bands are filled with electrons, and these filled bands are known as valence band. There is a energy gap between this conduction band and the valence band. This gap is known as what? Forbidden energy gap. So conductors. So what is conductors? So in conductors, the conduction band and the valence band, that means the empty band and the filled bands are overlapped with each other. Okay, there is no energy gap between this conduction band and valence band. Therefore the electrons of this filled band can jump easily to the conduction band. Okay, and we know that when electrons move from one place to the another, then electricity is generated. So conductors can generate electricity easily, because here the movement of electron is easy, since there is no energy gap between the conduction band and valence band. So next one is what? Insulators. Okay, so what happened in insulators? So this one is what? Conduction band, and this one is what? Valence band. In case of the insulator, the energy gap between this valence band and conduction band is very large, so the electron of this valence band cannot jump to the conduction band. Okay, so there is no flow of electron, that means they cannot conduct electricity, that means they have a very small electrical conductivity. Next one is semiconductor. In semiconductor, the energy gap between this conduction band and the valence band is what? Very small. That's why some amount of electron from this valence band can jump to the conduction band. Okay, so movement of electron means what? They can conduct electricity. Okay, now if you increase the temperature, Okay, now if you increase the temperature, then the movement of electron will be more. Yes or no? So more of the electron will now jump to the conduction band, and because of this movement, the electrical conductivity will increase more. Okay, and because of this reason, semiconductor are again also known as what? Intrinsic semiconductors. Okay, and the substances like silicon, germanium, etc. show the behavior of semiconductors. Okay, now again the electrical conductivity of semiconductor can be increased by the process called doping. Okay, you already know what is doping. Doping means the addition of impurity or mixing of impurity. So by this process also we can increase the electrical conductivity of a semiconductors. Based on doping, semiconductors are classified into two parts. The first one is what? Electron rich impurities or n-type semiconductors. So in n-type semiconductor group, 14 elements are doped with group 15 elements. Okay, group 14 elements are doped with group 15 elements. For example, arsenic, phosphorus, etc. Okay, so for this type of semiconductor we took the perfect crystal of a group 14 element, that is silicon, because silicon is a group 14 element. And in case of group 14 element, there are total 4 valence electrons are there. So silicon has a 4 valence electron, 1 2 3 4, 1 2 3 4. So they this silicon has how many valential electron? 1 2 3 4. This silicon has also 1 2 3 4. So they will form a bond with each other to create this perfect crystal. Now this silicon will dope with arsenic or phosphorus, that means with the group 15 element. Okay, now in group 15 element there are total 5 number of valence electrons are there. Okay, so let us replace this silicon with this arsenic. Okay, so we replace here, and what we say, there are total 5 valence electrons in case of the arsenic. 1 2 3 4 5. Okay, now these 4 electrons, 1 2 3 4, they will used in the formation of a covalent bond with its neighboring silicon elements. Okay, but the fifth number of electrons is remains as what? Extra, and this is free here because it is not bonded with any type of atoms or with any electrons. So here this electron is free, so they will delocalize in this crystal, that means electrons will move in this crystal. Now what we got, that when electron moves, then they generate what? Electricity. So because of this delocalization, the electrical conductivity will increase. Okay, the electrical conductivity of doped silicon will increase. Okay, and this increase is because of this negative charge electron. That's why this is also known as what? N-type semiconductor. Here N is for negative charge, and this is electron rich because here the number of electron increases as before, because arsenic has 5 valence electron but silicon has only 4 valence electrons, so electron is increased as compared to the first crystal. Okay, the second type is electron deficient or p-type semiconductor. In p-type semiconductor group 14 elements are doped with group 13 elements. Okay, so here also we took the crystal of silicon, because here silicon is what? Group 14 element, and we know that in group 14 element there are total 4 valence electrons, and in case of the group 13 elements there are total 3 valence electrons are there. Okay, now for example boron, aluminium, etc. These are what? Group 13 elements. Okay, now this crystal will drop with group 13 element, say boron. Okay, so we replace this silicon with one of the boron atom, and what we said, in group 13 element there are only 3 electrons, 1 2 3. Okay, so at first these three electrons will participate in the formation of bond with this neighboring silicon atoms. Okay, and this place is what? Electron hole. That means this boron atom will create one of the electron hole. This hole will generate automatically. Okay, now since this is hole, that means what? This is a free space. Okay, so this electron now will try to move towards this hole. Okay, now if this electron moves to this hole, then electron will come here, and this place will now create what? New hole. Okay, this position is now what? New hole. Again this electron will go to or move towards this hole, and electron will be come here, and this position will again create what? New hole. Okay, so and the process will be continue like this. So the movement or the direction of the electron is in which direction? Direction of electron is in this direction, and the direction of this hole, electron hole, is in which direction? In this direction. So this will be the direction of hole. Okay, now this is what? Electron deficient. Now electron deficient means what? When we consider positive means what? Electron deficient, and negative means what? Electron rich. So here in semiconductor, this positive is considered as what? Hole. Okay, so this hole of electron will be considered as what? Positive hole. Okay, now here the number of electron will decrease because boron has only 3 valence electron, but silicon has 4 valence electron. So one of the electron is less in this crystal as compared to this crystal. Therefore this is what? Electron deficient. And this is called p type of semiconductor. P is for this positive charge. Okay, because of this hole the electrons can move. Yes, so movement of electron means what? Production of electricity. That means because of this hole the electrical conductivity of this crystal will increase. Okay. Magnetic properties of solids. Now magnetic properties of solids are classified into 5 parts: paramagnetism, diamagnetism, ferromagnetism, antiferromagnetism, and ferrimagnetism. Let's discuss one by one. First one is paramagnetism. So paramagnetisms are those substances which are weakly attracted by a magnetic field when applied in a magnetic field, and this is due to the presence of unpaired electron. Okay, and now suppose unpaired electron means what? In orbital they will be present like this. These are what? Unpaired electron. So here the magnetic moment will be not equal to 0 because the direction is in the same direction. Okay, example O2, copper 2, etc. We already studied in 11th that the O2 molecule has what? Unpaired electron. Likewise copper 2 plus has also unpaired electron. So they are known as what? Paramagnetism. Now next one is what? Diamagnetism. Now those substances which show diamagnetism are weakly repelled by a magnetic field. Okay, and they doesn't have unpaired electrons. Now doesn't have unpaired electron means what? The valence electrons are paired. Paired means what? One electron will be in a upper direction, another will be in a lower direction. So in diamagnetism mu will be equal to 0. That means magnetic moment will be equal to 0. Yes, because they cancel each other because both are in opposite direction. Now here in paramagnetism they are weakly attracted because in case of the paramagnetism the presence of the unpaired electron is very less. For example in O2 there are only 2 unpaired electrons are there, so they are weakly attracted by a magnetic field. Now next one is what? Ferromagnetism. Now what happened in ferromagnetism? First of all the metal, okay, the metal is act as what? Electron donor. That's why it will donate its one of the electron and will convert to what? plus plus, electron minus. Okay, that's why this metal will behave as a dipole. Dipole means what? Where positive and negative charges are there. So in metal also, M plus, that means positive charge, electron minus, that means negative charge, both are there. So it will act as what? Dipole. Okay, now when magnetic field is applied, then the ions of this metal will try to arrange themselves. Okay, and in ferromagnetism they arrange like this: plus minus, plus minus, plus minus, or in the same direction. This is the alignment of magnetic moment. Okay, now what you done? You applied the magnetic field. Now if you remove the magnetic field from these ions, then also the group of these ions will act as a tiny magnet. Okay, they convert to the permanent magnet. Okay, so these are known as what? Domains, means the group of ions they act, which acts as a tiny magnet, because we applied here the magnetic field. So this group of ions are known as what? Domains. Okay, an example are iron, cobalt, etc. And these substances are strongly attracted by a magnetic field. So next one is what? Antiferromagnetism. So in antiferromagnetism, the domains are arranged in this way. Okay, in a proper way. Plus minus, minus plus, plus minus. That means like this. One will be in a upper side, another will be in a lower side, upper side, lower side, like this, in a arranged in a proper way. Okay, so here the change in magnetic moment will be equal to 0, because they will cancel each other. One is in upper side, this will cancel this, this will cancel this, this will cancel this, like this. Okay, they will cancel each other. That's why this magnetic moment will be 0 in antiferromagnetism. Okay, and these are strongly repelled by a magnetic field. Examples are like manganese oxide, manganese dioxide, etc. Okay, and the last one is ferrimagnetism. So in ferrimagnetism, the domains are not arranged in a proper way. Okay, the domains in the substance are aligned in a parallel or anti-parallel direction in unequal numbers. For example, here both are in a upper direction, but only single arrow is in a lower direction, like this, in a unequal number. Okay, so in ferrimagnetic substance, this mu, that means the magnetic moment is not equal to 0. You will see some amount of the magnetic moment in ferrimagnetic substance. Okay, but this magnetic moment in a ferrimagnetic substances are lower than that of the ferromagnetic substances. Okay, and they are weakly attracted by magnetic field as compared to that of the ferromagnetic substances.